Hi, my name is Dan Crosson. I'm a Master's of Computer Science student at the University of Illinois at Urbana-Champaign, and this video is about database design. So database design is extremely relevant to the field of data engineering and still very important to the fields of data science and software engineering. Here's a list of courses at UIUC you can look into that cover at least partially some aspects of database design and important decisions around database design. Topics that I'm going to cover in this video include primary and foreign keys and normalization, and the goal of this video is to understand the fundamental decisions of database design and to generate avenues of interest for further learning. So relational databases, some examples of which are MySQL, PostgreSQL, and SQL Server, represent data in tables that visually somewhat resemble spreadsheets, where you have rows, columns, and each column is an attribute and each row is a record. The example we will use in this lesson is students and courses. We will use a pretty limited example. In the real world, obviously, designs get much more complicated, so getting a firm grasp of the fundamentals is really important. So for our example, we want to represent the student name, their major, their year, and then for courses we want to represent the title and the course subject, and then we want to also represent the grade a student received in a course. So the naive approach for storing this information is to throw it all in one table, where each row represents a student who took a course and received a grade. This approach is known as denormalization, and we will get into the specifics and the pros and cons of this approach in the following slide and also later on in the presentation. So the pros and cons of this approach, traditionally speaking, there are mostly cons. The most significant drawback of this approach is that there's significant data duplication. So each student's information is repeated in each row, and as we add more attributes to course and student information, this duplication gets worse and worse and makes database storage more and more wasteful, and also can do funny things with the analysis of data. And furthermore, when we want to go in and update data for a student or a course, we have to go to each row where that data is represented, which as database size increases will get incredibly expensive. The one upside of this approach is that all of our data is in one place, so we do not have to do any work to combine the course and student information. Again, we'll talk about this more later on in the presentation. So normalization is the process of separating data into multiple tables to reduce duplication. So if we apply normalization to this example, we might get something like this, where we have a student table with, the student's name, their major, and their year, and then we would have a course table with the course title and the subject. Now this generates a couple of questions. First of all, where did the grades go? We've lost the relationship between students, courses, and then therefore we don't have a way to represent their grades in those courses. So how do we relate the student table and the course table? And for that, we're going to need a couple of concepts. The first concept is a primary key. So most of the time in a relational database, we want to identify each record in the table by a unique identifier, which we call a primary key. A primary key must be unique to a record. So if a primary key shows up twice in a database table, the corresponding attributes for each row in which that ID appears must be exactly the same. If any of them are different, there's a violation of the primary key principle or rule, and your database system will get mad at you and yell at you and tell you that you have an error. This is especially helpful in the context of this example because many students can be named John Smith and major in computer science and be freshmen. So having a way to uniquely identify a student is extremely valuable. So how do we relate courses and students now that we have them uniquely identified? In this example, our best bet is to create another table that will contain a student ID, a course ID, and a grade in each row. So therefore, a row will signify that a student took a course and received a certain grade. The student ID and the course ID are called foreign keys, and typically these are primary keys of one table that are located in another table, and therefore create a relationship between those two tables. So by putting student ID in this third table, we are saying that the third table is related to the student table, and that in order to look up the corresponding record in the student table, we just have to use this student ID. So this is what we're left with. We have a student table with an ID, a name, a major, a year, and some data to fill out that table. Then we have a course table with an ID, a title, and a subject. And then we have this third table where we have a student ID, a course ID, and a grade. So the way to read that third table is that John Smith took data mining and received a B+. Now, there are significant advantages here because we have reduced essentially that first denormalized table into 3 attributes instead of, 5 or 6. And so as your database gets much larger in terms of the number of attributes for each student or course, there's significant savings because while the course and student tables will grow wider, the third table will not change in size. So we have significant data deduplication. But how do we extract information from this design? Essentially, we will have to do to combine tables together, and that process is called joining. Joins use a shared column between two tables to match rows of each table together. And as your database gets larger, this operation becomes increasingly expensive. So for an example, to calculate a student's GPA, we would simply join the student and course table to the third table on a student ID, and then take the average of their grades with some mathematical function, and we will get a GPA out of that. So again, I touched on this a little bit. The pro of this approach is deduplication, which makes storage more efficient and also makes data updates more easier to perform because we only have to go to one row. If we want to change John Smith's major to electrical engineering, we just have to go to John Smith's record in the student table and update that instead of having to search through every single row of that one big table at the beginning. The major drawback of this approach is joins. So each time we want to query information that somehow involves the relationship between these tables, we have to join them together, which gets very expensive as your data gets larger. So the solution to that problem is denormalization, which we talked about at the beginning. But you might be confused because we talked about how there were significant flaws with denormalization, including deduplication or data duplication. And the answer to that question is that the design you implement is heavily dependent upon your use case. So if we have an analytical use case, we might go with a denormalized approach with one big table to avoid having to join together multiple tables, which is an incredibly slow and expensive operation. Whereas if we have more transactional use case with a lot of updates and inserts, we might use a normalized approach to make those more efficient operations. So in conclusion, database design is really important to the efficient and accurate storage and analysis of data, and understanding the fundamentals of design is really crucial to working as a data engineer, but it's also important for data scientists and software engineers to understand so that they know how to write accurate queries to databases. Primary and foreign keys facilitate relationships between tables in relational databases and really make relational databases function. And just to note again that the specific design of a database should reflect the needs of your organization. I hope you found this video helpful. Thank you for your time.